Thank you. I'm Laura Ray, and I'm the interim dean at the Thayer School of Engineering. And I'd like to welcome each of you to this very special lecture in our weekly Jones Seminar series. I'm thrilled to formally introduce Professor Eric Fossum for his inaugural lecture as the new John H. Krehbiel Senior Professor for Emerging Technologies. But first, I'd like to acknowledge and thank John Krehbiel, known to many of us as Jake, who established this professorship 30 years ago. Jake has a deep and long-standing relationship with Dartmouth, its faculty and programs. He served on the Thayer board for 15 years from 1984 to 1999, including 12 years as chair, and along with his wife Karen, now serves on the President's Leadership Council. He's the father of 3 Dartmouth graduates, 2 of whom received their BE degrees from Thayer. Fred Pete Krehbiel, Dartmouth 87, Thayer 89. John Yaz Krehbiel III, Dartmouth 91, Thayer 92. And Margaret Meg Krehbiel, Dartmouth 94. As families go, the Krehbiels truly are a family of engineers. Jake's father, John Sr., for whom this professorship is named, never stopped being one. As a young engineer in the 1940s, John Sr. joined his father's company, Molex, to help design its first electrical components, and many of you use these components in your projects. Through the course of his career, he earned 14 patents for Molex. He never retired. He worked 5 days per week as the company CEO and as the head of the group that explored and researched future projects until his death at the age of 87. Over the years, the generosity of the Krehbiel family has helped the Thayer School grow as a center of innovation and has helped us remain at the forefront of important technological discovery in the engineering sciences. In establishing the Krehbiel professorship, Jake and his family wanted to honor John Sr. and his enduring spirit of innovation while supporting Thayer in its efforts to attract and retain faculty members whose scholarship presents new and exciting directions for engineering. In addition to supporting our faculty, Jake, along with his brother Fred, also created the Krehbiel Family Scholarship Fund, which has provided financial aid for 80 Dartmouth undergraduates since 1995. I can think of nobody who is more appropriate to hold this chair than Professor Eric Fossum, whose CMOS image sensor technology has literally transformed how we as a society document and share our everyday moments with one another, on our cell phones, webcams, and in many other devices. The camera-on-a-chip technology that he invented is now on more than 4 billion devices today. And I've been told that he will share with us a very special photograph that he has taken with one of those devices during his presentation. But that's just the beginning. Now, as one of the world's top image sensor experts, Eric and his former students and now colleagues have launched startup company GigaJot to develop new image capture technology currently not possible on today's devices. This continuing work on the Quanta Image Sensor will have powerful implications for medicine, national security and defense, computer imaging, and in helping us better experience and understanding space and the universe. As many of you know, in 2017, Eric was awarded the Queen Elizabeth Prize, considered the Nobel Prize of our field and one of the greatest honors to be bestowed on an engineer. He's a member of the National Academy of Engineering, a charter fellow of the National Academy of Inventors, and the National Inventors Hall of Fame inductee. He's a recipient of NASA's Exceptional Achievement Medal, an IEEE Andrew Grove Award and Medal, the Royal Photographic Society's Progress Medal, and the SMPTE Camera Origination and Imaging Medal, among many other honors. He is the author of more than 300 technical papers and holds 165 patents. In addition to being a premier scholar, teacher, entrepreneur, and mentor, Eric, as many of you know, is the director of the PhD Innovation Program at Thayer, and as Dartmouth's Associate Provost for Entrepreneurship and Technology Transfer. There's no better way to introduce Eric than through a medium to which he has himself contributed. The video that you are about to see shows the enormous impact of Eric's work and his work has already had and the impact that he will continue to have on this world.
So there's about 4 billion cameras made every year, over 100 cameras every second that use the CMOS image sensor technology. I mean, it's amazing to see people taking pictures all the time, and every now and then I was like, oh wait, I helped make that happen. It's kind of a surprise to me sometimes. So in 1990, when I was a professor at Columbia, I was recruited to the NASA Jet Propulsion Laboratory at the California Institute of Technology, Caltech. After I was at JPL for a couple of years, the administrator of NASA said, hey, we want to build smaller rockets, we want to have smaller instrument systems. And for me at JPL, it meant how do we build cameras that were maybe the size of a bread box or larger and shrink it down to a coffee cup size. It's pretty common for new technologies that are challenging an incumbent technology to have a long uphill battle. But the technology that really helped make the CMOS image sensor stick was the cell phone camera. What's amazing to me is how pervasive and ubiquitous the CMOS image sensor technology has become. When you do hands-on science, first of all, it's fun. So it's something you want to keep doing. But you also internalize a lot of the basic scientific principles. When you work on something in a hands-on way, you become intimately familiar with the problem and the solution at the same time. If you've got a good idea and it's meant to be, so to speak, you may not get it right the first time, but trying over and over again to get it right can often lead to success. So I was actually very lucky to find Dartmouth, and that gave me the opportunity to teach as well as do research with graduate students. I find it very satisfying to develop people, whether it's college students or it's fellow faculty members. It's all the same process, and it's equally rewarding at every level. I think at some point in everybody's life, you realize that you need to give back to society. One of the reasons that I really support Camp Invention is just the sheer fun that the kids are having in the inventive process. It feels very satisfying to me to feel like I've passed on my knowledge and what I've known and watched them thrive and grow up. I really enjoy working with the National Inventors Hall of Fame. First of all, because it's part of my identity as being an inventor. But more importantly, the Inventors Hall of Fame is a lot of giving back to society and the kind of passing on our experiences and learning to the next generation, and also sharing experiences among inventors and learning from each other is also a very important aspect of being part of the National Inventors Hall of Fame. I enjoy my job at Dartmouth very much, but I also need some downtime. There's something nice about being at a farm where you can actually viscerally do things. I really enjoyed a lot of hands-on activity myself. All this experiential learning that I've been talking about and hands-on activity is sort of reflected in some way in having this camera at your fingertips that you can, in a very hands-on way, interact with both your friends and family and the world and nature. And seeing people have fun with my technology really makes me happy.
So please welcome me and welcome Eric Fossum, the John H. Krehbiel Senior Professor of Emerging Technologies, for his inaugural lecture, A Camera in Every Pocket.
But I can't put this on. There we go. Well, first of all, I want to say thank you to the Krehbiel family for their generosity to making education so strong at Dartmouth. And I have to say also that when I first was informed that in my honor I got to prepare a talk for all of you and give a talk, I was kind of wondering about that. But but actually seeing all your faces and seeing so many people from around the campus, and it really is an honor to be able to speak to you about the work that I've been doing. So thank you so much for attending. So anyway, hey, you all have my technology in your pocket for sure. There's probably a couple of chips using the CMOS sensor technology in your smartphone these days. And people love to take pictures. This cracked me up. Okay, it was like, why would people go see the Mona Lisa to take a picture of the Mona Lisa? But I guess there's something in the human psyche. We want to share our experiences and let people know we've been there or something like that, or just somehow feel like you've captured a part of that scene forever for yourself. But wow, it's just that exponential curve we always talk about in entrepreneurship. This is just the number of CMOS sensors that have been sold year to year. So we're up at about $13 or $14 billion per year, and about 5.5 billion units. So that's more than the 4 billion you heard a few minutes ago. It keeps going up. And so that works out to be about 170-something cameras per second, 24/7 being manufactured. So as I tell students, not only is there a conveyor belt somewhere with 174 cameras per second going by, so fast you couldn't even see it, in 5 years there'll be another conveyor belt with 175 cameras going by, going in the landfill. So we need to, think about that as engineers. So anyway, people take a lot of pictures, and up at the top is I found this information about the number of uploaded pictures per day in billions. And being a good engineer, I put it on a semi-log plot, and it's it's like a 2x per year trend, which means that if you carried this out to this year, it'd be over 10 billion pictures per day, perhaps, uploaded to the internet. That's an amazing number. I mean, it's just completely mind-boggling. Probably half are about cats. Yeah. Ironically, my daughter, who's in this lower right picture, is working at Instagram. She tells me she hasn't told anybody there what her dad did. I don't know what that means. But, it's great that we get to use this technology regularly. She's out in California. You can see she's pregnant. She was pregnant in that picture. And I got this picture just 2 days ago. So, it's slightly surreal to think that I get to see pictures of my granddaughter, first granddaughter, like from California, minutes after the picture is taken. And yet I had something to do with that technology. It's just kind of like, wow, that was very clever of me to plan that out. Okay, so in this talk, I want to tell you kind of 3 subject, or 4, maybe 5, I don't know, things. But I want to start with a little bit of science because that's my job as a professor. So just a couple things that you might want to know about science for imaging. So the first is that photons are very small quanta of light, very, very small amounts of energy. And of course, the wavelength of the photon, so to speak, is dependent on its energy, or the color. And just to give you an idea about how tiny a photon is in energy, a single 60-watt light bulb emits about 10 billion photons per second. So photons are really tiny, okay? Another fact about photons is that they're not well behaved, okay? They don't arrive from a light source evenly spaced. So it'd be nice if they just came out like the steady drip drip of a faucet, but instead they come out in bunches like traffic on the highway. So that means if you're trying to measure how much light is coming from something, it's kind of like trying to measure the traffic on the highway. So you cover your eyes, open them for a second or 10 seconds, close it, count the number of cars, and you know that's going to be a terrible estimate of the number of cars on the highway on average. It's just what you happen to see at that moment. Same thing with counting photons. So that leads to a variation or variance in the count, which is often called photon shot noise. And that shot noise could be if you just have a single collector of photons and look at many samples over time. You'll see that every sample is a little bit different. Or if you have a number of buckets collecting light, like in an image sensor, from different places, even though if they receive the same average light level, we'll see a variance across those pixels. And you can see this in your phone yourself. This is a picture I took, and you look at the gray area to the right there, and I think you can see it, that every pixel is a little bit different intensity, and that is photon shot noise. Even in the darker area in the top right, also the same phenomenon happens. So photons are noisy. And this is the most intense science slide that you'll see. Okay, so there's a image sensor chip, an old one that we built at Photobit. Top upper part, that grayish part, is I have a pointer. Is the actual imaging area. The rest is support circuitry. So when a photon comes into the sensor chip, it comes into the silicon, and silicon, as you know, is a very hard material. It's like diamond, very similar to diamond, covalently bonded silicon atoms to other silicon atoms. And when a photon comes in, though, if it has enough energy, it can actually break one of those bonds and set that electron that was in that covalent bond free. And if there's an electric field, that electron will wander away. Also interesting is that there's a broken bond left behind when that electron goes away. And we think it was a hole. It's not a very imaginative term, but it's called a hole. And that hole can also hop to the adjacent bond or another adjacent bond in the presence of an electric field. Of course, it's really the electrons in the bonds that are moving over, but actually it's a lot easier to think about that hole, just like we think about, if you happen to drink beer, you might be thinking about the bubbles in the beer. Or you will be next time you have a beer. Yeah, it's kind of like anti-gravity for bubbles in a beer, and these also go backwards. So we have electron hole pairs that are generated. We can show that in an energy diagram here. There's a conduction band and a valence band, and the photon comes in and excites an electron from the valence band up to the conduction band. What's also shown in this picture here, which is a pinned photodiode, is that we can modify the semiconductor by putting in charged impurities. And those charged impurities change the electrostatic potential inside the semiconductor according to how we place them. And so we can actually engineer a potential change across the semiconductor to whatever we want, practically. So think of this as like a swimming pool, which would be gravity instead of electrostatics. We can build this potential so that the electrons will roll down to the bottom of the pool here, and they'll just stay there until we do something else with them. So we can collect, we would call this a photoelectron because it's generated by a photon. We can collect these in the bottom of the pool until we're ready. Ready for what? We're reading them out. This is the second less intense slide. You'll see. Everything will be easier after this. So we have to somehow figure out how many electrons we got in our pixel. So we have these electrons, and we might send them to an amplifier. And an amplifier in this case would be a capacitor and a switch at the front, and then some amplification. So we would say connect this to a voltage of, pick a voltage, 3.3 volts. Close the switch, and then open the switch. And we would get a voltage of about 3.3 volts across the capacitor. If you're not electrical engineers, don't worry, we won't spend a lot of time on this. But the interesting thing is that it's only about 3.3 volts. And that's because there's always some uncertainty. When this switch is closed, I like to think of it as a bridge being closed, there's electrons going back and forth all the time between the capacitor and the power supply. And it's like people going, or cars going across this bridge. When you open it suddenly, there's always a few left on one side or the other side. It's never the same thing twice. So that gives always rise to a little variance. And for image sensors, where we're trying to worry about exactly counting the number of photoelectrons, that's a very vexing variance. Hey, I'm going to have to use that phrase more often. So vexing variance. A method was devised that was for CCDs, but Marvin White took that from radar processing called correlated double sampling. And the solution is the same solution you'd find at a deli counter. You're going to go buy some material. It's going to go in a container. When you buy it, you really don't want to pay for the material that you are buying. So you want the person behind the counter to weigh the container first, zero out the scale, and then put in the material that you're buying. So you're only paying for that amount. So we do that here too. So we reset this. We get some voltage that's different than the 3.3. It's at 3.302. We measure that. Then we transfer these electrons onto that capacitor. So that's changing the charge on the capacitor. So the voltage will also change. And then we measure the voltage the second time. So that's called correlated double sampling. And that's basically, we can measure the charge by taking the difference between those two voltages, just like you would on a deli scale. That was the hard part for this talk. Okay. So let's move on to image sensors. I think by now you all know that image sensors are used in many, many different places. Of course, the killer app for the technology is the cell phone camera. But they're used in DSLRs and regular cameras. Had a chance to work on a couple of interesting biomedical imaging things over the years, especially in the early days. One is dental X-ray sensors. Probably all of you go to the dentist these days, and they put this sensor in your mouth, and they shoot the X-ray at it, and immediately you can see on the screen the image, which is quite different than the old days, where they put film in your mouth, and then have to go develop the film while you've got gauze and everything stuffed in your mouth. It was very unpleasant. Plus, there's a lot of chemical usage. So this is pretty good. This was an idea that came from a very small company in New York, approached us and said, could you do this? And we said, yes, we can. And it's like taking over the world of dentistry, pretty much. Very high market penetration now. Another one is this Israeli idea. A couple of missile scientists came up with this idea. I guess they were no longer missile scientists. And said, could we build a little tiny missile that would go through your body and take pictures? So they had the idea for this pill camera, but the technology at the time couldn't make this thing work because it would require, the pill would be too big. You don't want to swallow some gigantic pill. And also the power would be enormous. It wouldn't even last for very long. But the CMOS image sensor technology enabled this, and now this is a very common diagnostic tool. And of course, used in backup cameras and drones. And this is a camera that's in the back of the mirror, and it may control the headlights, for example, for automatic dimming. So we worked on that as well, too, at the back at the dawn of CMOS image sensors. Speaking of dawns of CMOS image sensors have been around for 50-something years. There was some very early work on MOS devices by Peter Noble and Gene Weckler, Peter in the UK, Gene in the US. And they actually built some very small arrays of sensors. Unfortunately, at that time, that technology was not very stable. MOS, CMOS, this wasn't CMOS, but NMOS was very new, and you could never get the same result twice in a row. So it was very hard to make that work. Fortunately, in 1969, the charge-coupled device, CCD, was invented at Bell Labs and solved all those instability problems that the previous work had and became quite popular. CCD works by shifting charge after it's generated by light, shifting it many, many times, and then down this way to an amplifier, just like the amplifier we were just talking about, that uses correlated double sampling. The trouble is that in order to make this work, you have to shift the charge thousands of times at high speed to get it out, and you can't really lose any electrons. So that's very tricky. It's like having a football field full of people that are measuring rain with buckets, and when you get done, you say, okay, everybody pass the water in your bucket to the person to the right, and everybody starts passing it like some big bucket brigade, and then it gets to the edge of the field, and you have to pass it down this way, and someone with a measuring stick is down at the corner of the field. And you could work out back in a backwards way what the rainfall was across the field. Electrons are trickier than that even, but again, you can't lose many. So to me, a CCD is kind of a miracle device, just like a 747. Now, you can't believe it could actually work, but it did work, and people made it work quite well. So here's an early CCD camera from Bell Labs after the CCD was invented. This is Steve Sasson. You saw him with me at the Inventors Hall of Fame taking our selfie together with Mo Rocca. He invented the self-contained digital camera in '75. This is a Galileo CCD camera, RCA camcorder, some industrial camera in the 80s. And you know what these cameras all have in common? First of all, they're big. Okay. The CCD chip actually is still quite small. But the problem with CCD is that you had all these other electronics to make it work. You had electronics to kind of push the charge along, and you also had electronics to measure the charge when it comes out. And if you put all that together with power supplies and everything, it makes for quite a big camera. Probably near the end of the CCD era, we got to this size, a camcorder. But still, if you remember camcorders in those days, you had to change the battery pretty often in order to take a family or home movie. So that wasn't too good. So big, take a lot of power, and also very tricky to make them work right. So NASA was using this technology when I went to JPL in the 1990s. So this is the Cassini spacecraft, and you can see the camera is this big thing. But here's a person down here in the lower left, in case you missed that. So these cameras are gigantic by the time you get done building them for space. So that was a kind of a problem. It made everything made these spacecraft huge. So faster, better, cheaper was what we were aiming for, as you heard in the National Inventors Hall of Fame film. They take great pictures. There's a lovely picture of Saturn from up near the, you can see the North Pole of Saturn. And, some amazing things, too. I don't know if you can just make this out, but perhaps blow up. You look at the top, it's like a hexagon. Who would think that there would be this cloud formation, atmospheric formation, that looks so much like a hexagon? We just keep discovering really incredible things out there, partly due to having camera technology out there. I loved working at JPL, by the way. It was like a great place to work. So much fun. Anyway, we had those gigantic cameras with all that electronics. And if you're an electrical engineer, it's like, what's the solution to big, massive boards of electronics? Well, integrate all that stuff on the same chip. But the problem was the recipe to make a CCD is quite different than the recipe to make regular mainstream microelectronics. And it's very hard to combine those two. It's like trying to bake a pie cake. It's just really hard to do the two things at the same time. So if we wanted to integrate the electronics, then we had to figure out how to make a good image sensor in the mainstream CMOS process. So that was the question. And so I decided to use the same basic approach, and we just put this whole circuit inside every single pixel. So it required intrapixel charge transfer and that correlated double sampling thing. Once we were able to show that worked well, we were able to build chips with a lot of integrated electronics, the so-called camera on a chip. Hey, that's my finger, by the way. Camera on a chip, which makes these cameras in your cell phone so small and leads to all those giant numbers, like 5 billion cameras per year. So that was the invention, really. I worked in a federally funded R&D center, and so we wanted to transfer this technology that was paid for by U.S. taxpayers out to U.S. industry and help U.S. industry. And I went around to a lot of companies trying to get them to adopt this technology, to license it from JPL or Caltech. Caltech runs JPL. And I just could not get anyone to bite. It was very difficult, including Kodak, by the way. They were interested, but not ready to move. So, I don't know, my personality. Many of you know my personality by now, so it's just like, heck, we're just going to do it ourselves because no one else is doing it. So we started a company, Sabrina Kemeny, Nick Dudamopoulos, Bob Nixon, and myself, started a company called Photobit in 1995 to see if we could make something of it. So anyway, after a while, we call it perspiration phase, I guess. It's like the less glamorous phase of a startup is like when you really actually have to make something work. So we grew to about 135 people, and there's another 100 patent applications filed to really turn this into a product. So even though we licensed maybe 3 or 4 patents from Caltech, it takes a lot more innovation before you're able to really launch a product. And we talked about all these things already. There's just a picture of the group that's somewhere, not at the end, but early 2000 in Pasadena. And then, oh yeah, did I mention that we sold the company? Yeah, so in 2001 we were acquired by Micron. So that was kind of Miller time for us. So anyway, after that, the technology developed a life of its own, I guess is the best way to put it. And the fact that it became so good and so ubiquitous has to do with the fact that there were thousands of engineers around the world working on this. So they still use the underlying intellectual property that we developed at JPL, but they made it work really well and really cheap so that you could use it in lots of places. So, and then Caltech also successfully enforced its patents against all the major players. I can only estimate it, but I think they probably earned about $150 million in license royalty fees from this technology. So they did well. Really well. But anyway, and then the funny thing is that NASA's now just adopting the technology for use in space. I mean, the automotive industry is very slow, and space is really, really slow for adopting technology. But anyway, the Mars 2020 mission, there's going to be like 24, 25 cameras on this vehicle, and all use CMOS image sensor technology. So I feel quite happy about that. So anyway, years go by, and it's used everywhere, and finally, thanks in large part to Joe Helbley, who thought that there was an opportunity that we should apply for, which was the Queen Elizabeth Prize. In fact, we received this. Mike Thompson, who was at Bell Labs doing the CCD along with George Smith, Nobu Teranishi, who did that swimming pool device we were talking about, the pin photodiode, and myself, and got to go to Buckingham Palace, which was fun. I mean, what can I say? Although it actually looks a lot like all the movie shots you've ever seen. It's like they really like the color red in there and gold. And then I just share a couple other pictures. This is leaving Buckingham Palace. It's Nobu. He was dressed in traditional Japanese dress. And this is the famous portico outside the palace, or it's still inside. But this picture was actually, you're not allowed to take any pictures there. They're very strict. So I didn't want to get my cell phone confiscated, so didn't want to get hers. But Frances Arnold, who just recently won the Nobel Prize, she was there. And so she snapped this picture for us and didn't do her any harm at all. So I feel kind of foolish for going so slowly. Lord John Brown gave us also those little shiny medals. So he was the former head of British Petroleum. And this was in Guildhall. And I'm happy to say that Joe Helbley made the effort to attend as well. And we also met with some Dartmouth alums in London, and that was also fun. But the best picture ever was taken by Joe Helbley with the help of my wife, who's sitting in the middle here, trying not to laugh too much. Hey. I think that there's a technical error somewhere because I still see it here on my screen. Okay, we're back. There's the picture. Sue claims that Joe egged her on. Joe doesn't bear any responsibility for it. Just happened to shoot a picture with action in the background. But anyway, I love that picture. That's great. Okay, so one serious topic I did want to talk about is the what happens when you have new technology. You've got all kinds of issues that come up. We don't have time. We could talk for an hour about this. Certainly privacy, security, and other things. Actually, the one that I feel the best about, which is a new issue, which is social justice. We now have the capability, since there's so many cameras out there, that when people are dragged off United Airline flights or whatever, there's almost always someone around with a cell phone camera to capture it. And that's really kind of changing the scene, and it's something I feel very good about. I also, incidentally, ran a MEMS company for a couple of years called Simpel, and here's some cool stuff we did. It was for autofocus modules for cell phone cameras. But eventually I got to Dartmouth, and I want to tell you about the work here. So you remember that photons are tiny quanta of energy. And so when I was running the MEMS company, I actually was still thinking about imaging, and someone had asked me to write the last chapter of a book on digital still cameras about the future. And so I was thinking about that, and I was thinking, well, what's the limit for image sensors? And the limit is kind of, what if we could only have that storage well, that swimming pool, what if it could only hold one electron? It was so small, you could just hold one electron. That's kind of the minimum that you can do. And how would we go about building an image sensor based on pixels that only have one electron or 0 electrons? So started thinking about that, and kind of came up with this idea, which now called the Quanta Image Sensor. And you can imagine that these pixels could be coded as 0 and 1, whether or not there was a photoelectron that was captured in the swimming pool, or there wasn't, 1 or 0. So we collect that binary data, but what if we had like a lot of pixels? What if we had like 1 billion pixels on a chip? And by the way, these pixels are very special because they're either detecting a 0 or 1, basically. So they're smaller than small. So had to give them a different name. So we call them a jot, which is Greek for smallest thing. And you'll see that we can actually create image pixels from lots of jots. So jots are smaller than pixels. So what if we had 1 billion on a chip, and what if we could read this out like 1,000 times per second, and then we have all this binary data. It's kind of like a scene out of the Matrix with all those ones and zeros going by. I mean, how could we combine that data and then reconstitute a grayscale image, right? So maybe we'd take some neighborhood of that jot data and use it to generate 1 pixel in the grayscale image. So that was kind of the vision. I will point out that 1 billion jots read out at 1,000 frames per second is a terabit per second of data, which is a big number. And also, I have to count single photons. And also, by the way, someday I'd like to see it in your pocket, so it needs to consume less than a watt. And this is like impossible in 2004, but it was a concept. So when I came to Dartmouth, and here's my group, except for Caitlin, who's not yet been photoshopped into this. A couple of these guys are photoshopped in. I was like, wow, what a great kind of forever project. I mean, I could work on this forever. And, we'll learn a lot of stuff along the way, but it'll be really interesting. So we started working on it, and it actually works, by the way. So I think, don't worry about this too much, but the arrival of photons into a pixel is best described by Poisson Process, which means, as we were talking about with shot noise, sometimes a lot arrive and sometimes none arrive. All depends upon your luck. But you can describe the probability of a certain number of arrivals. And then what we care about for a jot is only 2 states of interest. One, that there was no photon that arrived, and the other that at least 1 photon arrived, which is just 1 minus the probability of no photons arriving. So we can plot that bit density, number of jots that have been hit per unit area or something like that, as a function of the exposure. And this is the average arrivals per jot. So think about it. Think about like watching raindrops hit a tiled patio. You know, at first, you know, there's a tile hit over here and another tile hit here, et cetera. But then some tiles get hit more than once. And eventually there's kind of that lucky tile that takes a long time to finally get hit with a raindrop. And that's the same thing that happens here, that eventually they'll all get occupied, but near the end, there's this kind of, 1 to the 1 minus e to the minus h behavior as we hit all the shots. So that's kind of interesting, because that gives us, in our exposure, instead of saturating, we get this extra so-called overexposure latitude, that we can accommodate brighter light without saturating our sensor. We can replot that same plot. I just changed it to a log scale down here. So this is the linear part and then the overexposure part up here. And we have this S-shaped characteristic, which is kind of interesting. This is maybe one of the favorite parts of my talk here for me, is that if you go back in literature to 1890, which is a long time ago, 1890, longer than Joe has been dean at Thayer, you will find that there is that film or plate emulsion has exactly the same characteristic. And why is that? Well, that's because film is made up of lots of little halide particles, I guess you could think about it. And if, I'm going to simplify this a little bit, but if a grain is hit by a photon, and then you develop the film later, it either washes away or it stays behind. It's kind of a binary thing. It was either hit by a photon or it wasn't hit by a photon. And so the density of film has exactly the same sort of statistical behavior and has the same characteristic as this Quanta Image Sensor proposal. And photographers are really interested in that because they hate my other technology. Not so much anymore because a lot of them are dying out. But you know, the old technology would go up and saturate right away. It didn't have any latitude in the exposure. So that gave digital imaging a completely different feel to the image compared to film. And you can see that right away. You can tell right away it was something that was shot in video or it was shot on film if you look at a movie, just from, it's kind of a gestalt feeling to the tone. Anyway, there's a lot of pull from that and also from cinematographers, so that was kind of cool. I'm not sure there's any money there, by the way, but there's a lot of pull. So I'm going to tell you, just set you up for experimental results. If you have an amplifier that is looking at electrons, like we were talking about, then let's say you have an average of 2 electrons per jot on average, and you just make a histogram of how many times I got what voltage out of my amplifier. Well, if there's no noise, then some of the time you will have exactly 0 results. Other times you'll have 1 photoelectron or 2 photoelectrons or 3. It's very discrete, okay, because electrons are discrete, so it's got to be very discrete voltages that you get out. But if you add a little bit of noise, then it kind of broadens these delta functions, and there's some chance you'll get a voltage that's not quite right on the discrete number. So that's about 0.12 electrons RMS read noise. If you go up to 0.25, they broaden more. And if you look at it more so, by the time you get up to 1 electron RMS read noise, which sounds pretty good, the noise in my sensor is only 1 electron, actually you can't see any quantization at all. So you have to be down maybe around 0.35 or lower to start to see this effect. And for our circuit, then, what we have to do is just put a comparator here, and it's like the voltage is less than this number, halfway point, we count it as a 0, digital 0, and if it's more than this, we count it as a digital 1. And that's our binary output, 0 or a 1. So we're now in the binary land. We can think about bit error rate. And if you have a 0.3 electrons RMS read noise, you will be wrong about 1 out of 20 times in your decision. If you can go down to 0.15 electrons RMS, the noise effect of the noise drops dramatically, and you're down at almost 100 times less bit error rate. So moving the noise between these two places can be very significant in terms of accuracy of photon counting. So how do we do our photon counting? Well, just went back to the same trick that worked before. Do this correlated double sampling, and the only trick is that we make this capacitor really, really small. So if it's like 160 attofarads, we can maybe see a millivolt if we put one electron on there. And a millivolt is starting to get to be a number that we can manage in a circuit. How do we get such a small capacitance? Okay, well, this is where the deeper part of the work that took us several years to do takes place. But basically, we had to invent a new kind of detector device. I did this with J.J. Ma, who's one of my students. And I would say that it's unusual for me to have inventions that are like 50-50 with one of my students in terms of contribution. And J.J. was definitely in this category. So I just want to acknowledge how important it is to find good students, make things work. So anyway, I want to explain how this device works, but basically it's a new device, and we simulated it. It seemed like it was going to work. And then you have to read it out. So here's that device in a circuit sort of diagram, and then after that, we want to measure the voltage on that Delhi scale or that node, and we use a source follower circuit to measure the voltage, which is pretty standard. I will point out that we do have this interesting problem that you have this source follower transistor, which I've drawn schematically here, and I know not everybody here, most people here don't understand what this is, but it's electrons basically are going from the source to the drain in this device, and like photons, which are noisy, these electrons in a transistor are also noisy. They don't flow uniformly. They flow, there might be some turbulence or something that's going on. And that gives rise to what we call 1 over F noise. So as a function of frequency, there's a lot of noise. And unfortunately for us, the power of the 1 over F noise goes like 1 over the gate area. So the smaller you make the gate, the more noise power you get. Why is that bad? Well, in terms of the small capacitance we need, we want to make this gate really small. But if we make it small, then the noise goes up. So we kind of have this trade-off, which is a nuisance, but just remind you what that curve looks like. So experimentally, if we do this, we get some very nice results. We can really clearly see quantization of electrons. This is, by the way, this is at room temperature and no avalanche, for those of you who know what that is. As we move from an average exposure of 1 electron per pixel to 2 to 3 to 4, these peak heights exactly follow what Poisson statistics says they should be. It's quite nice. Here's for an average of 8. And so for some people, knowing how many photons were collected is extremely important for things like quantum encryption. So this photon number, being able to do this with a kind of semi-conventional technology could be quite important down the road. Not to mention low-light imaging. Dakota Starkey, who may or may not be here somewhere, but anyway, hey, there he is. He's holding up the column. I mean, did this modeling work, and it just shows it's really such a good fit, in fact, that we can extract a lot of data from this. Like, we can measure the read noise from this. Remember I told you that this amount of envelope depends on the noise. If we just measure it, we can measure the noise to within 1/100th of an electron quite accurately. I'm not sure what that's good for, but it's cool that we can do that. We built this device in what's called a stacked backside illuminated CMOS image sensor process. So this is not our chip that built, because we're not allowed to cut our chip apart and show it to anybody because of the foundry that made it. But somebody else cut up a Sony chip. And let me just take you through the layer. There's actually 2 chips that this is cross-section, so this is cutting the cake in a slice. And then another chip down here in cross-section. here's actually 3 chips that they can also do, but we're just talking about 2 right now, pixels and circuits. And so the top chip is up here, and there are some micro lenses on top that help guide the light into the pixels. There are red, green, blue filters. Oh, well, you can't tell that they're red, green, and blue, but I know that. Up on the top here. And then these are the actual pixels where the charge is collected, and they're isolated from each other by actually cutting the silicon between the pixels. Some of that readout electronics. Then this very dense bonding between wafer layers, which is, this could be just a couple of microns, for example, spacing, which is a major innovation just in the past few years. Nothing that was happening already, so we just used that. And then additional layer of electronics for further processing. So we made something where we used a stacked cluster parallel readout where we have a lot of pixels in a cluster, and then underneath or in the shadow of the cluster is all the readout electronics for that cluster. So it's very easy to replicate this and make bigger and bigger arrays just by replicating this structure. And it has some very good benefits as far as parasitics and things like that. So here's a picture of the chip that, well, I say we made, but actually this was fabricated by the Taiwan Semiconductor Manufacturing Corporation in Taiwan, who did us a big favor by making this chip for us. My understanding is that if we tried to make this chip ourselves, it would be at least $500,000 we'd have to pay, but they donated this to us. I will mention that the CEO of TSMC is my former lab mate from Yale. Which just goes to show you that you need to choose your lab mates carefully. So we're very grateful to TSMC for doing this. This is actually, each one of these black squares is 1 million pixels. And so we did 20 different design variations on this chip. And you can see those 20 different, so it's actually 20 million pixels on this chip. Yeah, you can read some of these things if you care, but all different design variations. So then we built, after we built the chip, we put it in a camera, and then we decided to take a picture of I took this picture once before with my camera, printed it out. We pointed our new camera, quiz camera, at this leopard, and lo and behold, it actually works. Holy cow. You know, the trouble with graduate students is that they want to finish and get out, right? So they just get to this point, and they're like writing a thesis and leaving. So this is the main reason for starting a startup, okay, is to try to continue to engage with those brilliant Dartmouth students over time. I'm saying that slightly facetiously, but it's really great that both JJ and Saleh, who did that work, started a spinoff with me called GigaJob. I'm also a co-founder in the company, but I'm like the silent partner, I guess. So anyway, started this company. Obviously, this type of technology is a platform technology. If we can count photons, we can think about all different sorts of things, security systems, low light vision. I think it'd be useful in the Internet of Things for very low light. Biological imaging for life sciences, where you have very weak fluorescent signals and things. Astronomy for sure. Possibly quantum cryptography. There's a lot of interest on that side. And of course, photography, cinematography, and maybe more things. So they took that chip and they actually built a, let's call it a more professional camera around it. Here's the camera right here. So that's a megapixel photon counting camera. And you take a picture with it. So here's a picture. This is taken, obviously, of a test scene, but the average exposure per pixel is just under 1 photon or 1 electron per pixel. And so, of course, there's lots of photon shot noise, as we were talking about, because photons hit some places and not others. Yeah, I lied to you a little bit. Not only are we doing single-bit jots, we're doing multi-bit jots so that you might be able to count 3 or 4 or 5 electrons in the pixel, not just 1. Gives us a little more flexibility. So this is a 3-bit device. You can see a histogram. You can still see the individual quantization in the histogram. So that's nice. But, you know, this quantum image sensor concept is not just the hardware. There's a computational part to it I was talking about at the beginning of how do you take these pixels in a cubicle or whatever we called it and create a grayscale image. And there's a lot of work going on this now because now we're just being able to start to actually realize these devices. So we're working with Purdue, and they helped us, or actually, I should say, a Purdue student came and worked for Gigajot and did this work. But anyway, so if you apply that computational imaging to this, I just want to show you what it does to the image. I hope you can see the difference where you're sitting. So again, this is the original image was about 0.87 electrons on average per pixel, and cleaned up it looks like this. What does that mean? That means those, have you ever seen night vision goggles for the military or something with all the fuzzy stuff going on? We can apply some processing, computational imaging to, along with this device, maybe integrated on the same chip, and produce this kind of imagery instead. So lots of really interesting applications start to happen. So just to wrap up here, I want to say that a few words about innovation. So if you think about it, there's kind of this, I don't know, this is a very simplified diagram, I know. But, you know, mostly we do research on things in graduate school. And every now and then you have an idea or discovery, invention that happens. And this is really the start of being able to do technology transfer and make something of it, innovation. So often there are some patents that come out of that work. Of course, we're producing, I should draw like fireworks going left and right, papers and conference talks and things like that. That's important too, to communicate to the world. But in terms of creating an enterprise, patents are really key. And then once you have intellectual property secure, you can think about either licensing it elsewhere or more importantly, do some sort of startup, like Gigajot or some other kind of many startups that we have coming out of Thayer these days. I look around the room and see a half a dozen right away. And you have to incubate this startup. It needs a lot of TLC as a startup starts, and then maybe some early stage funding, and you have this growth take off. So just 2 points here. One is technology transfer. We have a technology transfer office here at Dartmouth. Technology transfer, though, is not just about giving somebody a patent and licensing them or writing a paper and saying, here you go, I've told you everything there is to know about this, go with it. Because that usually never works right. People want more information. They need know-how to make it work. And like you saw with my example of Photobit, my own personal example, is that sometimes you try to do that and people don't even understand what it's good for or not ready to do it or whatever. And it's really up to the people, especially the inventors, to have the drive to carry that technology forward and make something of it. All right? So this entrepreneurship and startup thing is a very important part of the whole innovation process, in fact. The second point that I want to make also is that to make this work well, you need a continuum of incubation. You can't just say, oh, Brian, wherever you are. You can't just like say, hey, oh, you invented something, you started a company, you're out of here. Go somewhere else, okay? Go up to DRTC. You really need that to work better. You need that same environment and that same chemistry for a while as that company, that embryonic company starts to grow and create. So this continuum of incubation is something that I really would like to work towards here at Dartmouth, so it's more of a continuum. And by the way, just to advertise, our PhD innovation program teaches our students this stuff down at the bottom, all this core stuff. So I'm very pleased to also be involved with so many great students in teaching them about this process. So I'm at the end. I just want to, of course, thank my students, faculty colleagues, support. We got a lot of financial support from a company, Rambus, also TSMC. We got a little bit of support from DARPA for whatever it was, a year. That was a strange story, let me tell you. And then, of course, the GigaJob's getting SVR support from NSF, NASA, and DOE, and some private funds as well. So thank you for letting me share my journey with you, and happy to answer questions if you like.
We have time for some few questions.
Don't be shy.
This involves some basic physics, and it may be not a very inviting question. Why does gate size and noise, why are they inversely related?
Yeah, excellent question. It has to do what's causing the noise, which may be trapped charge or fluctuations. And if you have a large gate area, they kind of average out better. And if you have a smaller gate area, they don't average out so well. And so the apparent power is higher. Rahul?
You gave this very interesting point that 0.16 femtofarads and 1 electron on a millivolt.
I hope I did the math right, but yes?
Yeah, I'm sure you did. So I got me thinking, well, if I put 1 electron on a hydrogen atom, which makes 13.6 volts with an energy level, that's about 10 to the minus 20 farads. And the numbers seem to work out right, because you're in a millivolt, and that would be 13.6 volts. And very early in your talk, you also said how really a bond is broken in silicon, when you make the electrons pair. So that just got me thinking, you think there's a way to get to having, maybe not hydrogen atoms, but few atoms in the jar, where a bond is broken, and rather than a millivolt, you're getting a larger voltage that's sort of amplified, maybe in a cascade or something, that you report that could push us further, sort of like the eye does with the photon breaking a bond and then making 1 photon give you 5 million electrons.
Well, I think you answered your own question right there. So I think that, sure, I think there's a lot of interesting possibilities. Of course, some people also detect by using avalanche to also generate more charge, get more gain. Lots of problems with that, which I have some backup slides to talk about if anybody wants. But yeah, I think, but one problem with just having a few atoms is that the probability of photon absorption could be pretty low, right? If you think about it, it's much better to have, I forget what the number is, but let's say it's 10 to the 12th or higher number of silicon atoms that can absorb the photon rather than a few, as you were suggesting. So that would be one possible issue with what you're saying. But sure, why not? I think we're at the beginning. I mean, it's like for me, it's like a rebirth of imaging. It's like, wow, we do stuff with single photons now. There's all kinds of new things we can do. And it's, well, I feel like I'm going on a big circle of life, but it's pretty interesting to be back at the beginning again. Brian?
Is there some value in dynamic range for this? Like the eye can see over 10 or so orders of magnitude. Would this technology have improvements or benefits in sort of wider dynamic range as well?
Wider, I'm not sure, but we can do probably about 120 or 130 dB dynamic range with this kind of device, which I didn't get into, but and that's usually more than a optical system can deliver. Usually a lot of stray light scattered in a lens system, so you can't even take advantage of that big dynamic range most of the time. So I think we can get there. I'm sure we can get there with this technology. Yep.
So I understand that you can kind of tell statistically the difference between 0 and 1 photons, but what's your quantum efficiency on the actual sensor? And then what kind of spectral range can you actually detect?
Right. So silicon has to absorb across that band gap, and that limits us to basically the visible spectrum, maybe a little bit in the near infrared. And in the device I'm showing you here, the quantum efficiency peaks at about 86 or 87% at 500 nanometers. Pretty good, by the way. And that's because of the backside illumination. You don't have anything blocking the light coming in, and it's the right thickness. Yes?
You mentioned on one of your slides, I didn't really comment, but the absorption of different colors of light in silicon goes with that.
Yes.
So I know there are some sensors that utilize it like pixels below pixel, but I believe they were on CMOS, on CCD technology. So is there anything like that in CMOS and possibly in Gigajot?
Right. So I'm going to answer your question in a slightly longer way. So when the device that you're talking about was Foveon was the most popular one. That was a CMOS sensor, not a CCD. When we did our attempts to do technology transfer out of JPL, one of the places we went to was National Semi. And National Semiconductor had, somebody I've drawn a blank on his name, Dick Merrill. I was one of our team partners there along with another guy. So after we finished transferring the technology to National Semiconductor, both those guys left National and both started image sensor companies. Okay? So so Dick Merrill went and co-founded Foveon along with a few other people, and then also got Carver Mead very interested in that. And they were able to, with Federico Fagin, they were able to draw in a lot of money. So they sunk about $140 million into that company, Foveon, and failed, basically. And the reason it has to do with that KTC noise, that capacitor noise I was talking about. When you go to that multi-level idea of using silicon as a filter itself, because silicon could be a filter, to get the different colors, you get that read noise. You lose the ability to do that correlated double sampling. So they always had trouble with noise, and also the fill factor of the pixels was a lot lower. So I told those guys it wasn't going to work out well. But I wasn't sure. Maybe they were going to kill me in the marketplace. But in fact, they died. So they were bought by Sigma for pennies on the dollar.
Any other questions?
Yes, one right here.
So far, it seemed like you were just differentiating between no electrons versus one and more.
Right.
Have you found it useful to differentiate between 0, 1 interaction, 2 interactions, etc.?
I might have a backup slide for that. So this is back to the curve we were looking at. So we can build a comparator or quantizer circuit with multiple comparison points and then discriminate between 0, 1, 2, and 3 or more photons. This would be a 2-bit multi-bit jot, for example. And the example I showed you, that picture, that was a 3-bit multi-bit device. So the answer is yes.
Any other questions?
Rahul?
You were at one of those computations in the dark, or something else, moving into the dark better than static into
Yes.
very high astronaut from moving.
Yeah. So again, that was one of the things that was beyond my time limit for the talk. But when we're talking about this cube of ones and zeros, and then making a cubicle, that cubicle doesn't have to be down the time axis perpendicularly. It could be skewed to track an object that's moving. So it's like time delay integration. And so for better or worse, another group in Scotland, even though I told them we could do that, they actually proved it first in a lab and showed some very nice imagery of de-blurring objects and getting a good resolution under very low light. So the answer is yes, absolutely. And in fact, you can have multiple tracks for multiple objects in the scene. So it's kind of a defense-related thing. There was a question over here, yes?
I was just curious about whether you've ever looked at biological systems for inspiration. I mean, I was thinking about when I was mentioning the dynamic range of your eye. Your dog's nose has unbelievable dynamic range in the sensor without saturating and still being able to discriminate? How do they do that? Do you look at that sort of thing and?
Well, those are two different things. The eye has got kind of a slow adaptation along with a regular transfer curve, and I have no clue how a nose works, although you probably know, or Joe knows, or something, but that molecular detection I'm not sure about, and I'm just a semiconductor guy, so I don't know. There you go.
Well, our time is running short here, so we're going to conclude the lecture and thank Eric, and please join us.